Hello, grade 12. This is physical science. My name is Gillian, and today we are tackling that huge topic of work energy power. We're going to look at the big ideas only because this is such a big section and quite tricky. We're going to look at those areas specifically that I think might help you in these exams. So let's have a look at our screen and our overview and check out what this whole section encompasses and what we're going to have time for today. So work energy power. Well, obviously it involves work, and there's specific definitions around this that we need to know, and along with those definitions comes this formula. We then have to look at the work energy theorem, which is imperative. It is really, really important to know what is going on with this, that should be an NB, with this particular section. We then have a look at energy, and involved in this section is the law of conservation of energy, and then our understanding of what is mechanical energy. We do need to have a look at conservative forces and non-conservative forces and the non-conservative work that comes out of that. And then there is a section of power. Now, power we will not have time for. Hopefully in the consolidation lesson we'll get to some problems around power. I will encourage you strongly to go and look at the videos that have been preset for you on this section. They are worthwhile, they are very detailed, detail that I cannot give you today in this lesson. So let's start with work. So now work is very specific in the sciences. So we think that when we are doing exercise and we're doing work biologically, that we're actually doing work. However, in terms of science, there's a very specific definition. So we could be pushing a pram along the ground, and it could be going at a constant velocity. In terms of science, I'm not actually doing work because there is no acceleration. The work that I do doesn't exist in terms of science. In terms of biology, yes, because my muscles are working. So let's have a look at this definition in terms of science, the scientific definition of work. It says the work done on an object by a force is the product of the displacement and the component of the force parallel to the displacement. Okay, so there has to be a force exerted onto the object. The object has to be displaced, there has to be movement, and it has to be, the force has to be parallel to the direction of movement, to the direction of displacement. What springs to mind here is what we've done in the past, which is when we have an object that has a force applied to it at an angle. So let's have a look there. There's my angle, okay. And what we've done is we have separated this applied force into its components. And we have a component which is horizontal, and we have a component which is vertical. So we draw in our lines here to get a right-angled triangle. This would be the horizontal component, and that would be the vertical component of this force that is applied. We would then use cos and sine rule to determine those values of the components. Okay, so when we're talking about components, it might be one of these components, a vertical component, horizontal component, or if we're on a slope, it might be the parallel component and the perpendicular component. Okay, this work that is done is measured in joules. It is a scalar quantity So it means that it is magnitude only. Now, the interesting thing about work is that it can be a negative value. And the reason why it can be a negative value is because work can be done against the system. So if we have something like friction that is working against the movement of an object, work is done to overcome that friction. In other words, friction is removing work from the system. It's removing work that should have been done in an ideal situation to move the object. It's taking away from that system. So if work is taking away from the system, then we have a value which is negative. Okay, so this negative refers to work that's being taken out of a system. Let's look then at the equation that comes out of our understanding of work. So work done is the same as energy transferred. Okay, so energy transferred, we need energy in order to do work, and energy is usually transferred when we are doing work. So it's quite an interesting relationship. Both are measured in joules. So the work done on an object by a constant force F is this. So the force times delta x times the cos of the theta, where force is the magnitude, so where F is the magnitude of the force, so that's how big. Delta x stands for the distance that has been covered by the object, or the displacement. So displacement is it's the change in displacement, the change in the distance that the object has moved. So that's the movement of the object. And theta is then speaking about the angle between the force and the displacement. So sometimes these forces are not direct forces, as we've seen earlier where I've drawn the components to the force. It's done at an angle. So we need to accommodate the angle at which the force is being applied to give us the displacement. And so that is accommodated by the cos of theta in this formula. The net work done on an object can be calculated by applying the definition of work, and it can be done in two ways. So we can the first way is we could either calculate the work done by each force in the system. So obviously there are a number of forces that can be working in a system, gravity, friction, an applied force. So all those forces together are doing work. We could find the work that is done by each individual force, so that's acting on this object, while the object is being displaced, and then we combine them, then we add them up. So we combine all the work of these individual forces and we add them together. The other way of doing it is by finding the net force that's acting on the object. So we can find the net force, and then once we found the net force, we can substitute it into this equation. So it's more of a two-step calculation when we are applying this work, this net work done. Okay, so I think to look at this and see how we can do it, we're going to have a look at a problem. So a force of 120 newtons is acting at 60 degrees to the horizontal. This accelerates a box, so there is acceleration at 30, the box has a mass of 30 kilograms along a horizontal of 100 meters. So I always like to draw a diagram. It helps me figure out what is going on. So if my horizontal is here, they're telling me that I have a force that's acting at 60 degrees to the horizontal. So there's my horizontal, the dotted line. So 60 degrees to the horizontal is this force that's 120 newtons. The box is, oh, we can't see that color. Let me change the color. So the box is 30 kilograms. Okay, I think I've got everything that I know. Oh no, what about the displacement? So the displacement would be 100 meters. Okay, calculate the net work done on the box if the force of friction, oh, look at this, is 25 newtons. So we've got a force of friction. So I'm going to use the second method of calculating this. I am going to first of all figure out what the net force is on this system, and then I'm going to use the net force and I'm going to pop it into this equation to calculate the net work done on this box. So let's work out, first of all, our net force. So net force, what is the net force on this box? It is going to be the force of the component. So let's just draw this in again. So we've got this horizontal component. We've got a force at 120 Newton. We have got an angle of 60 degrees. So if I fill in there, I have a right angled triangle. What is going to be giving me the movement for this box? It's going to be the horizontal component of the force. So there, the horizontal component. So it's going to be the horizontal component plus the frictional force, right? That's going to give me the net force on the system. How do I calculate the horizontal component? Well, I'm going to use my sine or cos rule. Let's have a look. I've got this FH, the horizontal component is the adjacent side, and so that is going to be cos. I need to use cos of theta. So I will have my force which is applied, cos, 60 degrees, plus, now my frictional force they told me was 25 newtons. We know that it is going to be a negative value. Why? Because it's acting against the direction of motion. So the box is moving this way under the influence of this applied force, or the horizontal component of the applied force. What's happening? Frictional force is moving in the opposite direction, and so I need to place this as minus 25 newtons. What is the applied force? It's 120 cos of 60 degrees minus 25. And my answer, I'm not going to show you on the calculator because we have a time issue, but I have calculated it as 35 Newton. So that is my net force. Right, grade 12s. Time has run out in this first segment. It is time for a break. When you come back, we'll have a look at the second part of working out this net work done. Welcome back, grade 12s. We're continuing. Right, we've calculated the net force on the system. It's 35 newtons. We're not done yet. The question was, calculate the net work done in the system. So we have to use this formula. W net equals the net force times the change in displacement times by cos theta. So we've already calculated what the net force is. It's 35 newtons. We know what the change in displacement is. It's been told us, given to us, it was 100 meters, remember? So we're going to put in there 100 meters. Now we need to cos the theta. Now what is this theta all about? This theta is telling us the difference, the degree difference between the displacement, so the direction of the displacement, and the applied force, or the net force. Now, in this case, it's net force, right? Because we've already discussed, we've found out what the total net force is. The net force is going to be in the direction of movement. So there is no difference between the displacement and the net force. The difference is 0. So that's what we have to write here. The angle between the net force and the direction of the displacement. So the direction of displacement and the net force are in the same direction. There is no difference in that degree. So it is naught. It is naught. Our answer here is, when you pop cos naught into your calculator, it comes up as +1. And so the answer here is 3,500 joules. Excellent. I hope that has helped you with how to approach these kind of problems. Sometimes you do get a problem where you are led through calculating the individual work done by each individual force acting on that object. And then at the end, all you have to do is add them all together. Let's move on to energy. So mechanical energy and understanding mechanical energy is key to understanding the vocabulary, the words that are used in questions. So mechanical energy is referring to kinetic energy, and it's referring to potential energy. Now, kinetic energy and potential energy are related. So as we lift an object up, it will gain, doesn't gain, energy is transferred to potential energy. As that object is dropped, the potential energy is converted to kinetic energy. And so they have a very close relationship. We know that kinetic energy has a formula of 1/2 mv squared. That's really important. And it's about the velocity of an object. Potential energy has a formula of mgh, and that is about the height of the object above the Earth. It is also involving the acceleration due to gravity, so gravitational acceleration. These two energies, as I said before, they convert. So one converts to the other, and so kinetic energy into potential energy into kinetic energy. When we're dealing with these mechanical energies, so both of them are the mechanical energies, when we are dealing with them, we normally refer to it as an isolated system. In other words, it's only those two energies. We ignore resistance, like air resistance. If we did not ignore it, then part of the energy would be removed from the system and would be converted into heat or light or sound. And you might experience that sometimes when you hear a golf ball being hit. Okay, you can hear that some of that energy is being converted into sound energy. You can actually hear it. And maybe that ball would also be warm because there is air friction depending on how hard you hit that ball. When we're talking about an isolated system, so no friction, the force on that isolated system, the net force is 0. It's really, really important that you bear that in mind. Okay, so the net force on an isolated system is equal to 0. This brings us to these two big words, so conservative and non-conservative. So if you think about the word conservative, conserve, it is conserving the energy of the system. And so conservative force is a force that will do work in moving an object and between 2 points, that's the definition, between 2 points. But the important thing is it's independent on the path taken. For example, gravity. So we've looked at problems where we've had an object that is moved along a level ground, a horizontal ground, and we've also looked at problems where we've had an object move on a slope. Now, in this case, the action of gravity doesn't change. So it doesn't matter whether the object is horizontal or whether it is on a slope, the action of gravity is still going to be there. We know that we then turn this force into parallel, F parallel to the slope and F perpendicular, and that's how we work out the components. But this gravity does not depend on the path. So when we have a conservative force that is acting, then we speak about the work done as being conservative work. When we are speaking about other forces that take away energy from a system, like friction, definitely friction, then we are talking about a non-conservative force. It's called a non-conservative force. It definitely does depend on the path taken. So if you imagine yourself falling on an astroturf or on the carpet or on the grass, it does depend, the welt that you get, the carpet burn that you get, does depend on how long and how far you've been in contact with the surface. So the further you ski along the astroturf, the bigger that burn is going to be. You know about that. So a non-conservative force is dependent on the path taken. And a big one here is friction. So friction is a non-conservative force. It depends on how far the object is on the surface, sliding on the surface, so it depends on the path, and the work that results from that is called non-conservative work. That brings us to this very, very, very important formula or relationship. So this NC stands for non-conservative. And what is it doing? It is taking energy out of the system. So it is a relationship in terms of the change in kinetic energy. So we can write this as a half mv final squared minus a half mv initial squared. Yes, so that is the change in kinetic energy plus mgh, the final, minus mg h, the initial. That is initial height. So that is the change in the potential energy. So if friction is taking energy out of the system, there has to be a change. But it is important that you recognize it's the change in kinetic energy plus the change in the potential energy. Remember the squares here. It is really, really important that you remember those squares. Right, grade 12s. That is really all we have time for today. Unfortunately, we are going to have a look at a question involving the non-conservative work done in a system. We're going to look at that question in our consolidation lesson. Please join me for that so that we can work through this, and particularly the details that you need to put into your calculations. Grade 12s, hope to see you next time.